All right, so let's get going. What is this? Is that an eraser? Oh, it is. Weird. Um, okay, so let me just quickly review where we were. Wait, is it three? Wait, these clocks don't agree with my computer. Presumably my computer is more accurate, right? Yeah. All right, well now it's 3:10 anyway. Okay, so let me briefly review what we were doing. All right, so of course this is the last week of the course, so we're finally sort of trying to put everything together a bit. Of course, I'm going to skip lots of details for things, but I will be able to, um, uh, I think I will be able to explain how various of these threads fit together. Both the, yeah, so anyway, let me say. So remember, so the goal, we said this, so we're finding analogs. We want to find analogs for the Einstein vacuum equations of Christodoulou's solutions. Of Christodoulou's. All right, and we of course there were two class of solutions of Christodoulou. There were the so-called scale invariant ones and the self-similar ones. We're starting with the simpler things, right? Okay, and all right, and then well, we want to use all this stuff that we spent all this time developing through the term for the vacuum equation, so i.e. double null foliations. And so our starting point, so we're going to look for some metrics um, in, um, in the double null form. Right. And we're going to put the shift sort of, I'm going to put in the U direction. All right. And then what we said, okay, we know, so starting motivated by the Christodoulou story. So we put something, so this is going to be the origin of our, oh, I should have said the final thing is that, right, and our starting point for all of this is that we assume that this thing generates the self-similarity, meaning that for this vector field, the Lie derivative of G equals 2 times G. All right, and then that imposed, then we talked about all the scaling numerology of all of the Ricci coefficients and metric components and all of that fun stuff. All right, and then we wanted to construct this thing. So we said this thing is flat, and we have this hypersurface V equals 0. And then we know, so there's sort of nothing going on here. And then what we expect from the Christodoulou solutions is that something that non-trivial emerges here. We expect the first derivative, well, in Christodoulou setting, the first derivative of the metric jumps. We'll see if that corresponds to something here or not. Okay, and then all right, and then we saw that, well, along v equals 0, write the Ricci-Duri equation in the E3 direction, this became some equation because exactly on this null hypersurface, the orbits of this dilation field are exactly tangent to this hypersurface. If you have an equation along this hypersurface, and if everything has some scaling, you sort of immediately won't be true if and only if some equation on the sphere is true. And so you get some equation, for, well, it involves the shift vector, it's all, it involved the lapse and the G slash. We saw that this equation, it's just one equation, one scalar equation. So it should have a lot of freedom, but I sort of asserted to you and I gave some brief heuristics why there actually is a lot of rigidity in that equation, and there's not a lot. So it turns out that's reasonable. So we take as a solution to this, we just take something sort of easy. We're just going to take omega equals 1, b equals 0, and g slash, well, we'll just take this equal to the round u squared times the round metric base. Well, you could put whatever. Doesn't really make too much of a difference. I'll just write it. Let's not assume it's a round metric. We'll see that there's eventually there's a certain underlying kind of for what you pick, there's a certain for this thing you pick here, there's a certain underlying conformal invariance to the equations, and that it turns out that I'm not going to give any kind of detailed discussion of this, but the it turns out that the solutions, at least in this first ones that we're going to construct, what really only depend on there's a percent, because then you can do analog in higher dimensions, and there's again there's some metric that you pick on the section of this thing. It might be a higher dimensional thing, but the construction only depends on the conformal class of that thing in general. You can show that, and in this case of 3+1 dimensions, these cuts are S2s, and all metrics on S2 are conformal to the round sphere. So in reality, it's like not only can you sort of without loss of generality do this, you can even without loss of generality take this to just be the round metric. And the well, and briefly, um, since I will talk about later, I mean, we'll see that kind of once you have some kind of solution double null, I mean, a conformal change, what does it mean? How do you see these different conformal factors here? It just comes from, once you have a v equals 0 and you want to define the other, your other null directions to get your double null foliation, but you have that choice. If you remember when we did the when we described finding a double null foliation, I mean, it started with a choice of a sphere, right? There's some sphere that you first pick, and then you shoot out null things foliated by each of those. But you can change that sphere. And if you think changing that sphere, if you have some original u equals -1, you can take some u tilde, and then you just define it. You could define it to be some function of theta, over some function of theta over the u. That's just like writing it, you know, you understand. You can parametrize the new choice, the new spheres of as a graph of the old ones and get some formula like this. And then but then you see when you write if you're self-similar, when you relate these things, you get a conformal change. And that, all right, then you have to track how other stuff changes and stuff. But that's ultimately it corresponds to slicing things differently. It corresponds to conformal change here. All right, that was a little aside. Okay, let me keep going where we were. So I'm still just trying to quickly review. All right, so we started with this, and then we asked ourselves, well, what about, so these are kind of, you can think that these quantities here along v equals 0. So this is all along v equals 0. This fixes the tangential geometry along v equals 0. All right, but we, of course, want to go beyond that. We want to construct, what's going on here. Again, we're trying to use this. We've seen in the course and other settings that it's useful sometimes when you have a characteristic null hypersurface, there's this useful fact that you can, there's a way to compute sort of, not just the things restricted to this, but you can take sort of derivatives in the other direction, and you can compute. In fact, you can take arbitrarily many, and inductively, once you fix them at one point, there's some, inductive set of ODEs you can solve, or transport equations more accurately, that you can solve and determine everything. So then we said, okay, so we know that, if we fix the values of, say, of Ricci coefficients at, say, u equals -1, then we can solve, some transport equations to get psi, in fact, on all of, well, I should say u equals -1 intersect. So you just fix one sphere, and then you can solve all these transport equations to get it on all of this. And so you can ask yourself then, is the thing that I get, consistent with being self-similar? All right, that's our first thing you can do. All right, any questions? So I guess that's basically where we ended, I think, last time. All right, so let me keep my. No, we don't want that one. Okay, and now before I uh before we write out exactly what happens in the um, and very concretely when you do this, let's just discuss some general things about this. All right, so what you imagine is that so what we expect, you know, um, well, what will happen? Well, let me just say it like this. Expect. All right, so what will happen when we do this is the following. Yeah. Oh, I guess, sorry, there was one more thing I want to clarify. So we can solve these transport equations. Then we can ask two related things. Then we can ask two related things, two related questions. So one, is the solution or does the solution have, have an exactly self-similar behavior? Have an exactly. And then relatedly, we can also ask if it has a behavior sort of that's, less or the same level, well, less singular or the same, less singular or same as the self-similar rate. All right, meaning we did all the scaling numerology and we saw that sort of right for a Ricci coefficient, say in an orthonormal frame, they should be size 1 over u if it's self-similar. So okay, so the first thing is clear. I guess I should put question marks because these are questions. Right. So the first question is just saying if you put some data, for which data can you put so that you solve it and you get it that it looks like 1 over u, exactly an orthonormal frame. But you can also ask something a little sort of weaker, which is, maybe what I really care about, I'm going to prove estimates and things. And I don't know. Well, okay, whatever reason, maybe I can ask this weaker question that, right, maybe even if it's not exactly 1 over u, but it's like better, that maybe that's also fine because somehow um, that shouldn't disturb things too much. I mean, that's almost like it means when I zoom in really close to this thing, it's as if it was zero. Zero is sort of always allowed because zero is 0 times 1 over u. So if I kind of if my quantity is just bounded as I approach u equals 0, it's maybe that's sort of good enough. Might be. Anyway, so it's interesting to ask these two questions. All right, and we'll see that it also has implications for the way that we will construct these things and their stability properties. Okay, so now what will happen is when we do this is we will, have, say, ODEs. I always write ODEs, but sure, they're really transport equations. The transport equations that become ODEs for each angular coordinate. We will have transport equations um, of the form. Well, we'll get there. Okay, so let me sort of derive while we have this. So let's suppose we're trying to solve for some psi. Let's call it psi tilde just to denote it's the one that we kind of care about. All right, and then, well, and let's even start first with a signature. I guess we can make this really concrete. So, right, because again, so we already know from knowing those guys, we have that, right? So remember, we know that chi hat bar at v equals 0 is 0. We know that omega bar at v equals 0 is 0. We know that trace chi bar is 2 over u. I said this last time, right? Okay, so in particular, these are all of the quantities of signature 0. So these are all signature equals, sorry, not 0, signature equals 1 quantities. So the next thing to do would be to look at something of signatures 0, right? So you can assume psi tilde as signature equal to 0. And then, so then you know that your equation could look like, so when we discussed this when we did the formal jet thing, so you can, so if there's a curvature component on this one, you can substitute the curvature component comes somewhere else and you substitute that equation in and you eventually get some equation just involving Ricci coefficients, but which can look like the following. You can get angular derivative of some other Ricci coefficient, or you can get something which is proportional to a quadratic combination. All right, so this is just thinking about it abstractly. Of course, you can write it down very explicitly. But it's useful to think about this abstractly, why it has to have a good form. Yeah. It's not partial, it's a two. Sorry. Other questions? All right. So for s equals zero, all right. So anyway, we know that these things have signature constraints. But the first thing I want to say, this has s equals zero. We know that the s equals zero ones are eta, eta bar, excuse me, and torsion, right? But all of these are basically, equivalently, these are linear combinations of just torsion and angular derivatives of the laps, but we know the laps, right? We took the laps to be one. So these are actually all the same. So these are all the same. Which means somehow that, so all things of signature zero are just the same. So let's just pick your favorite one, denote that by psi tilde. Okay, so now let's look over here. So we know that, so this quantity here, this total thing is signature one, right? Because you apply noblet 3 raises it by 1. All right, so that's 1. Now you go here, angular derivatives don't do anything. So this one has to be signature 1. But in fact, the angular derivatives of things of signature 1, well, any angular operator applied to it will be something 0, basically, right? Because, well, these ones vanish, and then this is the only one that doesn't vanish, and that's something like spherically symmetric. Right? So get that. Okay, so then you get here. So these ones have to be some psi s1, right? Psi s2, where s1 plus s2 equals 1. And again, we've done these games now quite a few times, right? So then there are only so many ways that something that minus 1, 0, or 1 can add up to 1, right? So this has to be something, this has to be 0 and 1. So, right. So, so you can always switch the order. So it has to be like this. All right, but I just argued that effectively all the S1 ones are something either up to, and then psi tilde, basically. So I can write, so therefore I can write this as, so this has to be, this one we're solving for, plus some constant times, that's this thing. Well, in fact, in this case, 0. So I'm writing it because, well, in reality, there's some slightly more general versions. And so where this omega is like a function of theta. So in my head, I always remember that formula. But in this, we took it to be 1. So these are really just actually all the same. Yeah. So I can write this as psi tilde times something of signature 1. But the only thing non-zero of signature 1 is trace chi bar. So this actually has to be, okay. And so the upshot is that, well, this equation takes a very, has to take a pretty simple form, that it's just going to be, so upshot. It has to be, there's some magical numbers, some C times trace chi bar times this equals 0. All right, that's the only possibility. Okay. But now here's sort of a difference from this, the case where we did the formal, this sort of, for the characteristic initial value problem, which was, of course, very much distinguished from this problem, and that covered a finite range, right? All the things that we were doing, the null hypersurface there went from 0 to V naught. And V naught is fixed and finite. Here we're going all the way to 0, and things are singular at 0. So, and so the upshot is when you did in the previous situation, a term like this, we would sort of put on the right-hand side and declare that, it's lower order. This is something linear in psi tilde, so at most it grows exponentially or something, right? It's all good. But here, that's not all good, right? We're very much concerned with the exact polynomial scaling. It's not enough to say, oh, maybe it blows up like e to the 1 over e. I mean, that's disaster. Okay. However, it's still not that bad. I mean, we know exactly what this thing is, right? This is 2 over u. And so this is just equal to 2 c of, well, let me just write it like this so that we get it like this. All right. And so we get something like this. All right, so this is okay. And yeah, that's that. And right, and this you can simply, well, you can solve. So you know that, so Nabla 3 in principle involves the E3. That's the covariant derivative in the E3 direction, which in principle involves the shift vector, but the shift is 0 here. So that's also, this is just covariant derivative in the du direction. Anyway, this is all nothing that hard to solve here. And what you get is that psi tilde, the general solution to this, is just going to be you know, some constant alpha times, well, I don't know. Maybe alpha is a curvature component. I should use that. Some constant a times u to the uh, times u to the minus c. I'll write it like this. All right. So, all right, and now you see a pretty clear dichotomy or trichotomy if you're considering this question too about what happens. So in this case, so if you're interested in question one, then basically, so for question one, um, what will happen is that, well, everything depends on the value of c, of course, right? So if, oh, I should say this is in the orthonormal frame. Right, orthonormal frame is exact. So if this is a tensorial quantity, which these all are, right? These are all nabla A's, right? If I want to treat this like a scalar, you know, then I should work in a frame which is like nabla 3 of the frame is 0, but that's exactly going to be an orthonormal frame, right? So this will be in an orthonormal frame. I will get this. Well, I should say, of course, there's some prof. You can put some profile of say this. There was a question? No? Sorry, I hallucinated. Okay, so if c equals 1, then you have freedom. You know, basically you can put whatever. You can equivalently think, of course, this h of theta, which will be the same tensor of whatever type this is of course, I mean, you could think that you just set u equals -1, and you get that psi tilde at u equals -1 can be any constant just times some tensor. So if this, you have this freedom. So you can call this a self-similar freedom. Right? But no, in a sense, that's not, if you pick a random c, it's probably not going to be 1, right? And then again, for question 1, it's really a dichotomy. So again, so if c is not equal to 1, then you have to pick, then you have to take a equals 0. Right? I'll get, now in a second, I'll go back, I'll tell you, you know, well, in the specific case of this, right here, you actually get c equals 3. All right? And so that you can do that. All right, but again, I'm trying to start, before I get into specific numbers, explain the principles of this. All right, so then for question 2, right, it's just slightly more, okay, again, c equals 1. So in this case, what in reality is that c less than or equal to 1, you have freedom, right? So if right, if c, the smaller c, if c is less than or equal to 1, you'll be less than, and need a equals 0 for c greater than 1. Okay, so that's great. There's one more thing that I want to say, just somewhat looking ahead. There's a slight, you could also imagine, so in this particular case, it happens that there's nothing here. This thing is 0. But as that was just, we did a particular analysis here. But it could happen for other, in fact, if you do other signatures, it can happen for other quantities, and it's not that it can't, it does happen for other quantities that you end up having to look at a similar thing, but there's something here. Now, what you can imagine, so let's slightly generalize. All right, so you can imagine that you end up, so now let's divorce ourselves from the specific setting of this this s equals 0. That was to sort of motivate the type of equation you can see. Imagine you're going further in the system. You're looking at some things. So maybe you did s equals 0, and now you're looking at s equals -1, or maybe you're looking at curvature. Well, then you would write capital C. But anyway, so I mean, we could even, let's just write f to not wed ourselves to it being any particular component. So at some point, you go through a similar thing. Maybe, again, I mean, this argument about when you have a term which involves the same quantity again, signature considerations will tell you that it can only be trace chi-bar because these ones vanish. So, all right, so you imagine again, you're going to have some C over U. Uh, C over U times F. And then, but in general, you could imagine that you have some F. Okay. And now again, let's suppose, and then, well, all right. And then depending on what the quantity you're looking at, F will have some natural self-similar scaling. So a scaling that would be associated to it if it were exactly self-similar. So if F is a Ricci coefficient, it would be u to the -1. If it was curvature, it'd be u to the -2. If it was a derivative of a Ricci coefficient, it'd be u to the -2, et cetera, et cetera. So that's whatever, So let's say, that the sort of correct scaling, there's something, right? Something. And now, what you can imagine is that, and you imagine you're doing this inductively. And so F, you should think, comes from stuff you've already done, and assume that it's okay. And what you assume is that F is consistent. Okay, meaning, so in the context of question 1, so if we're looking at exact self-similarity, consistent should mean that F, is like u to the, it should be 1 worse. Okay, again, ignore him. Or in the context of question 2, F is at most as bad as that. Okay, and then again, you have a similar, so you get a similar kind of, set of things depending on if you hit this critical value of whatchamacallit, of U, of C, sorry. Depending if C takes these critical values, depending on whatever the scaling is, will determine different things. There's a slight, and I'll get to putting this F because there's a slight complication that can happen. So again, let's look at question 1. So question 1 is kind of interesting. So if, yeah, so let me just see the best way to write this. So what can happen is if you're at the, so the point is, so if, C is at the critical case, right? So then the general solution, so you write this as, so let's say you write it at, you have U to the, C is equal to D now. So you have this, right? Okay, and then you, so I conjugate it by the U to the D, and now I integrate, and then you want to integrate. Okay, but something happens. So what happens? There's a log, exactly. So this is the thing. So, and then integrate, but if F is not 0, you get a log generally. Get a log. Which is not consistent. All right, at least in this form that I did. All right, it turns out that, in reality, even that case, it's not the end of the story, actually. But at least in the framework that we've done, that kind of tells you that That's not good. That you would have to, I mean, you're just kind of the whole thing would break down because there's not like a choice, right? It's not like you can't fix, the kernel of this, the general solution of this is right, a specific and homogeneous solution plus something plus an arbitrary solution to the linear problem. The solution to the linear problem will always be at the right level, but it's the inhomogeneous one that's messed up. And so there's no way to cure this. So this is a disaster. All right, except that it turns out so some version of this problem, if you do the same construction in not in 3 plus 1, but if you go to 5 plus 1 or 7 plus 1 or 8 plus or 9 plus 1, if you go up in even increments, some version of this always happens. And there's a way to solve it, which involves that you have to allow, I mean, well, maybe not. Let me not get into it. I can say something later about it. Well, this class is focused on 3 plus 1. All right. I'll just say you have to violate some assumption that we did earlier to not get to here. But there's a way to deal with it. Okay. All right, that's that. And but otherwise, sort of story is the same. Otherwise, it's sort of similar story. So basically, if you're not at this, and also for Q2, I'll just say also for Q2. That is to say, so assuming this f has the right balance for either two of these versions, if so at the critical thing, if f is non-zero, it's not good because you get this log business. Otherwise, if you're interested in this one, and if c, if c is not at the critical thing, then well, maybe I should say a little more. All right, so if c, let's say if c is not equal to d, then you will uh, basically then you can get, so then the general solution, so the general solution will be something times, some a of theta, say times u um to the minus c, and then you get plus some, integrating this thing. So you get some u to the minus c times integral, say -1 up to u of u tilde times c, something like this, right? Okay, and so, all right. So then depending on so if you're doing question one that you want something exactly self-similar, so if C is not equal to D, well, you're not really going to have a total freedom here. You might think, oh, you set that to be 0, but that's not so simple, right? Because this integral, depending on what values here happen, right, there will be a piece that also behaves like the C. So you might want to pick this to sort of cancel that piece. And then there's a piece coming from depending on exactly what F is or some. Anyway, I'll just say it's not too difficult of an exercise to show that there'll be a unique choice of A which works. All right. All right, that's just from looking, like just, to make it concrete, you could just put like F equals u to the minus, well, pretend C is 1 and then put F equal a constant or something, right? Then you're going to get um, well, this as u goes to 0, this will just converge to some quantity, right? And so do the expansion. So it'll converge to -1 to 0 of u, and then the next term will be something big O of u going to 0. So, but that first term as you look at the integral, it'll be singular because you'll have u to the minus c times that integral. So then you would pick A to cancel that integral, and then the next term would be okay, et cetera, et cetera. Okay, well, 344. Okay, so that's that. All right, so that's one point of view. Now you can go through this with this system. Maybe, what do I want to say? I'm trying to decide. So there's another point of view. There's another way to think about these kind of these. So we're looking at all these things, basically like whether I have this freedom in this thing, and that corresponds to what values. Like I said, the value of this thing here, for example, in this case, this corresponds to setting u equals -1. So this freedom corresponds to a freedom here. There's another way to look at these problems, which so this is somehow, this way of looking, determining whether or not you have a freedom here, you can think of as it's somehow like, it's like a dynamical, it uses the whole space-time. Even though we have a self-similarity, we didn't quotient out by the self-similarity in a directed way, or use it. We just sort of started solving and saw if things were consistent with it. And that's related to why we're able to using this method, we can do this question 2 version. We don't have to work within exact self-similarity. But there is another, sometimes it's useful to think about when looking at exact self-similarity, there's an alternative approach to question 1. All right, so again, you can think, so you imagine you're in this, again, let's imagine we're in this kind of setting. All right. So this is now question 1. So let's assume that f has the right scaling. So assume that f, does scale like d to the minus 1, and you're in this setting. Now what you can do is you can say, so suppose, yeah, you can argue sort of this following way. It's a little weird. So you say, so suppose I had a self-similar solution. I mean, all of this stuff is we're just trying to find like constraints on whether, so it's reason, all of this is like, we haven't constructed anything yet. We're just trying to figure out what would be true if it existed, even all of this. So I say, suppose I had one, then f, so if f, remember by this d is what by definition is the scaling. So if f, then f, at least in an orthonormal frame, will look like u to the minus d, that's because that's its scaling degree. And then it will be times some, I don't know, I need to pick some number, something. Say v over u, then times some theta, depending on the theta thing, right? This is what it means, right? And the thing about this, so for such a function of this form, you can convert, and this we talked about, I talked about in the context of Christodoulou stuff already, that all equations, when you have a self-similar structure, you can convert, derivatives in a u or v direction to the other ones at the expense of sometimes strange weights. All right, so let's work that out here. So I don't lose anything by writing. U is negative, so maybe I'll just write it like this. All right, so let's look what happens here. So if I take du of f here, I'm going to get minus d, this to the minus d minus 1, but I'll get this, right? Times p, that's if the derivative hits that, right? And then I'm going to get plus, when the derivative hits this, so I'll get minus u to the minus d, then I get p, I'll put p prime, the prime will denote this derivative here, right? All right, and then du of this will give me minus v over u squared, right? On the other hand, dv of f just equals minus u minus d, again, times p prime times 1 over u, right? But just do the chain rule. All right, so then there's a relation between these. And so what I get is that, so therefore du of f equals d times minus u to the minus d. No, it just equals, sorry. It equals this times f, right? Because if I just take out the minus 1 and the d, then that's just what f was, right? And then I get this thing, but I'm going to keep this in mind. So then I'm going to write minus v over u times dv. Okay. In particular, if dv of f is, say, is continuous, that's an a priori assumption. So suppose that our solution is, say, C1, so that the derivatives make sense. And it has to be the case that when I set v equals 0, this goes away. Right. Okay. And so what's the point? So let's go. All right, so let's consider that this equate for, well, we can just do the general thing. All right, so we have this nabla 3 of f plus c over u f equals f, right? So if I'm self-similar, so if self-similar, well then, and I'm in an orthonormal frame, then this nabla 3 is just going to act like d by du in the orthonormal frame. And so the upshot is that, say at this equation, if everything is self-similar, this equation becomes, remember, so u is negative, right? So c over u is equal to minus c over minus u, right? So this equation then becomes d minus c, um, uh, d minus c equals this. Right? Again, this is just saying if you find one of these equations in the double null, while you're going through all of the equations, and if you know the right-hand side already behaves like something self-similar, and if you assume that the space-time is actually self-similar, then it must be the case, and you could convert this using that formula, then it must be the case that this equation is true, right? Now, this equation is, of course, completely algebraic, right? There's no derivatives anymore. And so now you can see sort of very clearly. Again, disadvantage, this is something you can only do using exact self-similarity, right? Advantage, it's completely algebraic and very clear now what's going on, right? So if D is not equal to C, then F is uniquely determined by F, which is what that was the conclusion up there, right? If D equals C and F is not 0, problem, right? Because 0 equals not 0. If D equals C and F equals 0, then freedom, self-similar freedom. Well, yeah, I'll just say freedom. Then you can put any F that's consistent with self-similarity, and you'll always get 0 equals 0. All right. So this is this alternative approach. So there are these both of these schemes are a way to analyze, with the caveat that this is restricted to exact self-similarity, are ways that you can go inductively through all the equations and derive all these things. So you can either think that you integrate ODEs, which is in some sense the better way to do, but there's something nice about this more rigid way of looking at it, because you get things that are, well, this is really algebraic. Okay, so now let me tell you what the conclusion is. Well, any questions?
There's 0.
Yeah, I mean, because everything we're doing is on v equals 0, right? We're trying to compute just like to infinite order the solution, but only on v equals 0. Well, then we'll have to do something more. It's all like one step at a time. Yeah, it's like the characteristic initial value. There's like it's this first way of getting some idea of what's going on. I mean, maybe it's worth saying, for example, if you're in the analytic category, so if your data is analytic, you could try to just sum the series. And in fact, that works. I mean, this is, if you look at what Pfefferman and Graham did, I mean, they do this. They say they do this again, some versions at higher dimensions. They don't work in this. They work in a different gauge, but whatever. They get some formal series. They compute formal series, and they show that, and in particular, if you're analytic, you can just sum it. Right. Of course, we don't want to. It's not in the context of relativity and hyperbolic PDE. It's quite unnatural to restrict to real analytic data. So we're not very satisfied with that from a PDE or a relativity perspective, but you can do that. But nevertheless, it's still very useful. It tells you what's going on. Okay, so now, all right. So what happens? Well, I already told you that. So for torsion, you do this process. You're going to get this. Right? So that three is bigger than 1, right? So this has to be 0. That means that there's no freedom there, and it has to be zero. So if you are trying to construct one of these scale invariant type solutions, and under the assumptions on the laps B and G slash that we did, you're going to have no hope. You better make sure that you a priori have set the torsion to be zero. Okay. Now let me look at the. Oh yeah, I wrote. All right. Then the next equation that you can do. So then you can do trace chi. All right. And again, you just sort of plug in, you do this thing that you plug in what you know and you work it out. And what you end up with is this. You end up with nabla 3 of trace chi plus, yeah, you get 2 over u, trace chi, and then you end up with, yeah, minus 2 Gauss curvature, minus 2. This is like, I don't know, what's it? Gauss curvature like this over u squared. So this k slash, so remember I put this g slash metric. And then, so this notation in the self-similar world, I always mean the profile. The math ring means the profile. So like g slash is u squared times some fixed thing not depending on u, right? So k slash ring by this notational convention is the Gauss curvature of this thing. If you imagine that you're just doing on the sphere, then it's just one. Like I said, and secretly without loss of generality, you can be the sphere. Okay, you get this. So again, so this is bigger than 1. This is non-zero now. So we expect that there's a unique solution for this. And the unique solution is just, well, it's just kind of what it should be. It's yeah, just going to be minus 2. Yeah. Right. So in particular, in the case where you just pick the round metric, you get trace chi is just 2 over u, which is exactly what it is on Minkowski space. So this is still sort of, this is like a trivial value. So nothing sort of interesting happened. All right. Now the interesting thing happens at chi hat. So for chi hat, what you get is nabla 3 of chi hat plus 1 over u chi hat. So now you're sweating in your shoes, right? But then it's 0. So you relax. It's okay. All right, so this tells you that you have a total self-similar freedom for chi hat. This means chi hat is free formally. All right. Great, and maybe that's kind of a natural place to pause. All right, but before I pause, so I'll just say, okay, so this process now has, well, okay, then there's also yeah, there's also omega. And for this one, what you get is well, um, yeah, you basically get nabla 3 of omega equals 0. So you kind of have there are two choices. So again, if you're working with exact self-similarity, then it would force that omega was 0, but you have the freedom to add a constant to little omega. Remember, little is a Ricci coefficient, so the self-similar rate is 1 over u. So this it's 0 over u. 0 is less than 1. So you could add a constant, and if you were in the setting where you just want things to not be too singular, you have some freedom here. But there's not a genuine self-similar freedom here. All right, so this concludes all of the Ricci coefficients. And then what I'll discuss after the break, you might, like I said, we want to compute this is all the Ricci coefficients. You might want to compute the full, like I keep saying this word, full jet. So in particular, we maybe want to understand V derivatives, full V derivatives. And is there going to be more freedom? Is there not? And what I'll explain is that there's a general principle which tells you that basically, at some point, you shouldn't have um, you can have freedom at some point, like you have here, but when you take enough V derivatives of the system, the freedom has to stop at some point. And eventually everything will become like this case, that either if you're exactly self-similar, the thing is just, well, there might be a right-hand side. Basically, either it'll just be determined what it is, or if you're satisfied with these less singular things, they'll just be free in the less singular sense. Okay, but I'll explain that after so we'll reconvene at 4:10. All right, so let's keep going. All right, so now I want to talk about doing now higher derivatives. So the first point is that, well, some of these are kind of, so I did that word. So I guess I go here, right? Um, so lots of the Ricci coefficients simply have Nabla-4 equations. So those are sort of particularly easy to compute their Nabla-4 behavior. All right. So first of all, so what about, taking more v derivatives? So taking more dv derivatives. All right. So first of all, lots of Ricci coefficients just have Nabla-4 equations. So those are straightforward. So uh you know, so yeah, so trace chi bar, chi hat bar, omega bar, eta. These all just have Nabla-4 equations, which well, and trace chi, that's Richard Dury, which will directly relate, so the Nabla-4 of these guys will just be equal to some set of, again, if there's curvature, you can find some other equation, substitute the curvature. Okay. Again, you should actually work that out for yourself if you really want to understand it. But trust me that Nabla-4 of these guys will just equal something that we've already computed. All right. So there's nothing really to check there. So if the other things are okay, then, you just get some formula basically. um, okay. Of course, there's some of these missing ones. Of course, and then for these ones are the same as eta, again, up to some angular derivative of the laps. So in terms of higher derivatives of those, for dv derivatives of these, they're just going to be equal to dv derivatives of this times dv derivatives of this. But dv derivatives of this, I mean, okay, there's some commutator there. So, but effectively, you're worried you want when dv hits the laps, which is little omega. So, okay, and so dv derivatives of these are given by, by an understanding of you know, dv derivatives of eta and little omega. Okay. It's roughly. Um, okay. Um, Fine. So the ones that aren't, therefore, basically what we need to understand are omega and chi hat. No, this chi hat. Of course, if you look at the null structure equations, you might complain to me and say, well, doesn't chi hat has a Nabla-4 equation? But the Nabla-4 equation for chi hat involves a curvature component that you actually can't substitute out. So it's not really an equation. It's more like a definition of the curvature component. Okay. So, and in fact, it's kind of like, in some sense, chi hat, if you're thinking about a wave equation, chi hat sort of corresponds to, uh, chi hat corresponds to dv of your solution. So, wave equation is du of dv plus some stuff. There's no, in the wave equation, you can't find a dv. It really has to be du. That's sort of fundamental to it being a wave equation. Um, okay. Anyway, and so these ones, so again, so you have this structure. So, okay, that's what that is. But again, just for sake of time, I'm going to be a bit schematic. So the idea is, so you have some equation like this, right? Some c over uf maybe equals some stuff, right? Okay, and we want to understand higher v derivatives. Of course, we know what to do we talked about this very briefly, of course, because I've been trying to get through lots of things quickly. But to get higher v derivatives, what do we do? Well, we just should, in the formal jet computations, we just differentiate this with d by dv to derive an equation for dv of f, and then just proceed like we just did, right? Okay. Well, let's think about what happens in this commutator. So I can write, so even if f is scalar, well, and so I could do some things. First of all, I can multiply this through by the laps. It doesn't really, That's fine. That's just because remember, so nabla 3 is equal to 1 over this times the, times this sort of projected covariant derivative with respect to d by du plus the vector field B, right? Or if you want, maybe make it more explicit like that. Okay, so I can just multiply everything through by the lapse. The lapse is 1 on v equals 0, but I'm going to multiply it through before I differentiate. Okay, and then I can also, I can use those formulas for like commutators of derivatives, but I want to make it just really like clear. So I think it's easier to think about Lie derivatives because one thing we know is that if you take the Lie derivative with respect to v and the Lie derivative with respect to u, this is certainly 0, right? Coordinate derivatives commute, right? Okay, so even if this is tensorial, let's just convert it to, so I can write this as this then becomes Lie derivative of this, say plus Lie derivative of b times this plus some, stuff times f. I'll just leave it like that, right? This stuff comes from converting covariant derivatives. The Lie derivative just will involve the second fundamental form in the E3 direction, right? I'm going to convert back at the end, so it sort of, in a way, it doesn't matter too much what this is. All right, now I can apply d by dv. And now what you can see very clearly where the commutator things are. So when I do that, I'm going to get, Lie u plus Lie b of so there's this term, this is sort of the term I care about, the dv goes through, and then there's the commutator. But you see the commutator is just going to be Lie v Lie b acting on f, but this is just this is something angular, right? Because right, the term you get, because d by dv can hit the vector field b. And that might have some angular component. Well, we know that the dv derivative of v is actually, that's what torsion tells you. So you can, if we know what torsion is, we can compute that, but so this will be proportional to that zeta times some angular derivative of f. But the point is that it's an angular derivative of f, which we sort of already know. We're trying to, right? Okay. And then, all right, then you can get, well, there's the stuff times dv of f, and then you could get, of course, there could be dv of the stuff. Somehow that's also, this is something we don't care about because we already know what f is. In fact, we know what this, that's sort of lower order. And in reality, we already know what dv of the stuff is. But let me not explain why exactly. It's a good exercise to think of. Okay, and then other stuff that you know. And then you can, okay, well then there's this term, right? I forgot. There's the plus c over u. I get f. Well, sorry. This term in reality comes from some, so you have, this is c over 2 times some trace chi bar, right? That's where we got the 2 over u from. Okay, so then when you take this, right, you take this derivative, again, the derivative could hit this trace chi bar. That's going to be a term like this. Again, I sort of noted, see, trace chi bar already has an Appel-4 equation, so you know what that is. So this is all stuff that you know. You don't have to worry about solving for it. You already know it. And so in other words, the only thing that really that's important is if the dv hits this. Of course, this is just the same. You see, you sort of just have the same term that you kind of already have. Okay, and then the upshot, of course, so now, I mean, I multiplied through by well, I can put this lapse outside here. Right. And so what you see is that I commute it with dv, but because sort of the commutator here this produces something angular on f. And again, and this stuff that gets produced when I made this Lie derivative, that's going to be things depending on the second fundamental form, i.e. chi bar. And these I already know directly what their Appel-4 equations are. So in other words, all this stuff I already know too. The upshot is that I get an equation if I then restrict upshot. So I commute my equation and then restrict it again to v equals 0. I'm going to have something which looks basically exactly the same. So I have my Lie derivative f plus, then I'm going to get this thing again. Well, I can go back to my original version of this, and then I have some stuff. This is all known. maybe, I mean, it's a different known thing, F tilde. Right, and what was the point of this heuristic computation? It's just that this leading order part of this ODE, like the equation itself didn't change. So we've saw that what's very important is like you have this derivative term, then you have this low order term with the u, and what this number here is very important, right? And I claim that it doesn't change. You just get stuff that you already know is okay because of this stuff, and this thing looks the same. But there is something that changed in terms of interpreting this equation, which is that I took a derivative of this quantity. So its natural scaling degree has changed. Right? We know that whenever you take any derivative, the scaling degree goes down. And so sort of the C, which is scary, has changed. Because it's sort of like again, so let's make this something concrete. So for example, in the yeah, of course.
Not understanding. We have our Nabla-3 equation. It is not equivalent to, or I don't know. We cannot apply directly the derivative of
E by dv.
Yeah, on both sides using a commutator.
With the Nabla-3. Yeah. No, I'm just,
Yeah.
yeah, I just want to make it clear why when you do that, I just want to make it clear that the extra terms that are, like what's important is that you do this commutator. It's just this one, you can just see that the only thing you get here is something angular. So over here somewhere is something, so when dv hits this b, so there's some term here that's like torsion times f. But I already know torsion, well, in fact, torsion is 0. On v equals 0, it's 0. But I know what torsion is. Let's suppose it wasn't even. Anyway, it doesn't matter. I know what it is. And I know what f is already. So I'm just making it clear. As opposed if I just wrote Nabla-3, Nabla-4, you might wonder what terms are there. And you might wonder if when you do that commutator, at the end, you get some equation, this number changes. So because for example, like when you take if you look at the commutator of Nabla-4 and an angular derivative of f, this thing sort of can produce some extra angular derivative. So like the things in the commutator, you can get x. Well, I mean, you sort of see that happen even here. But here, if you think this covariant angular derivative is like, it's like r to the -1 times an angular derivative on the sphere or something, then the dv can hit the r, and you get another angular derivative. So sort of anyway, so there are things that sort of change. So if you have some equation like dv of f plus c over u f, and I apply a covariant derivative in it, then I don't get the same thing. I actually get this. The c will shift because these things have a non-trivial comment, like that dv can hit that r, you might think, and produces some more angular. So this thing actually shifts a bit. But the point is that here it doesn't shift. Well, again, it doesn't shift up the stuff I don't care about. I mean, because I can put that stuff on the other side. And I just did it in this way to make it manifest. Instead of just asserting, sort of. All right. And the point is, like I said, so the dv, if the scaling degree of f was d, then dv of this is well, I guess how do I forget my notation of scaling degree? Call it d if it's u to the -d, or let me just okay. So if it was supposed to be like this, right? Then what you expect for the self-similar thing is this, right? But the point is that like 1 power worse is okay. You see, so for example, so now let's make it even more concrete. So let's go, we had this equation, right? So we had this on v equals 0, right? Determine chi hat, we had a self-similar freedom. Now, as a result of this heuristic analysis, if I take a derivative, then I'm going to get that I look at one derivative of this, the equation doesn't change. Equals, okay, some stuff that scales correctly. Scales, right, it will scale correctly anyway, meaning, so in this case, so the normal scaling, if I take a derivative of chi hat, the normal scaling degree is that should behave like -2, and then I take a derivative, it's like -3. So all the stuff here will be like u to the -3. Okay, but now what you see is that this thing's natural scaling degree is -2, but before it was critical, but now it's in this, you might call it the subcritical range. Now the solution that the kernel of this ODE generates is something that's less singular than self-similar behavior. Right? And this is a fundamental principle. So what you can kind of see from this is that if I take, basically like d by dv, the kernel of the kind of transport equation stays the same, but the thing that I'm okay with is I become okay with more and more singular things from the point of view of scaling. And so basically, for example, in the 3+1 case, so we know there are only two real, because all of these other ones satisfy null before equations, we're only really concerned with these ones, right? And so what we see is the following, that this one was critical, it was right at the one. This one is already kind of good, in that we have zero over u here. Now, once I start hitting this with null befores, I'm going to always be above the critical thing, which means depending on which question I'm after. So if I want an exactly self-similar solution to this, that basically means there'll be a unique solution. Or if I allow the flexibility, all of the extra junk, if I just take the general solution, will actually be less singular than the bad rate, because the kernel of this, you can see, is good. And the same thing will happen here. Right. And that's kind of comforting because even if you want to solve these are ultimately some kind of wave equations, and there shouldn't be, it would be maybe a little disturbing if there was like infinitely many free. It's sort of saying that, so what you see is that if you're looking at exact self-similarity, once you pick this initial data, your data along v equals 0, which is basically just a choice of that g slash, that metric, then what you see is the only other choice is that you get to pick this chi hat. And you can roughly think of this as, it's like picking the solution and its derivative, then determine it. It kind of makes sense, right? And it turns out there's a similar, you can do the same thing in higher dimensions. It gets more, the equations are a bit more complicated, but you can, especially if you rely on kind of signature type analysis, you can do it in a not too bad of a way. And what's funny there is that the free term doesn't occur at one. So you pick this data just on v equals 0, like the g slash, lapse is 1, similar thing. Then you start doing all this stuff. And what you see is that this term won't be free at first. So the first free term that you see occurs at something like, so if your space-time dimension is well, now there are too many d. We have to call that d. What else can I call the space-time dimension? I could call it n, but don't you always do n+1? But then.
Space.
All right, I don't like that, but we're relativists. We don't talk about space. If it's space-time dimension d, forget about that. All right, if this is the space-time dimension, then okay, then this is the dimension of your surface, d minus 2. So in the regular case, this is 2. Then what happens is that you get a free term, which is basically at d minus 2. It's like what is it? It's basically d minus 2 over 2 derivatives is where you get this free term. So in particular, what you see is that when d is odd, the natural freedom is in some sense fractional. All right, which I haven't really told. There's a way to incorporate such things in this analysis. I didn't really explain, but ultimately it's similar. And in higher even dimensions, somehow it'll just be higher, But the analog of this equation, though, in higher, so you get to some even in the even dimensional case. So you have some version of this, except it occurs somehow after you take a bunch of derivatives. You eventually get something which hits the critical thing. And in that case, the thing on the right-hand side is not 0. And so you get this log thing, and you have to there's some way to renormalize out the log, but whatever. Okay, just wanted to briefly indicate that there's a more general kind of thing. Okay, so that's that. So what does this sort of suggest? So this suggests that, let's get back to sort of our more pedestrian considerations of 3+1 dimensions. And what it says is, okay, like we have this freedom, then higher V derivatives are just kind of, even if you sort of pick the wrong thing somehow, and you solve it, even if you don't pick the exact self-similar thing, it's kind of, it'll be not too singular. Okay. So what? All right, and that leads now to this following sort of plan for constructing these, which I'll now explain. All right, and this next step is not something that's obvious at all, but okay. So this leads us to the following plan for constructing the actual spacetime. We're constructing some actual spacetime. Okay, so let's draw our picture again. So we have our origin here. We have this v equals 0. So here I'm flat. Okay, so now what I want to do is I'm going to put something here. Imagine this is going to be u equals -1. Okay, and now what I'm going to do is I'm going to put data. Of course, this is a characteristic data, this thing we talked about so much. I'm going to put data on u equals -1, which is consistent. You know, with with having, well, say consistent with question 2, right? I having self-similar bounds. All right, so this is just this. All this is, I'm just saying, this is just a constraint at only at this point, right? I mean, the jet at this point. And here, so I'm just saying you kind of put. All right, so here we know. Here we know. I mean, right? So here is just whatever. This equals 1. This equals 0, right? G slash equals u squared times this. What the difficulty is, I want to try to construct something self-similar. So you might think, okay, I could put data here, do a characteristic value problem, but try to prove it exists in some region, or whatever. But I mean, but you sort of a priori, you have no idea what to put here. Okay, I was able to compute sort of, in principle, we can compute the jet to infinite order. You could try to, okay, in the analytic category, you could just sum it. You might say, all right, I don't know. I mean, you could put data here, which was consistent to infinite order. That's also kind of a pain. I mean, we want to close, we could work in Sobolev. I mean, our existence, everything we do, our estimates is all like out of some finite Sobolev space, right? We don't want to go to infinite order. That's kind of unreasonable. But here's this key thing. This is this key thing. Here it says, all right, if at some point, if you take enough v derivatives and you just stop, at some point, the noise is not that bad. Curiously. So even if I like don't, I start ignoring what the exact self-similar thing should be here at the jet. So at the level, in this case, it's not just abstractly in the jet. At the level of already one derivative of chi hat, i.e. two derivatives of the metric, already there, even if I put the wrong thing, as long as all my first derivatives did the right thing, the sort of the noise from this, the error from this is something which is slower than the self-similar rate. So you think, okay, maybe that's fine. Okay, and that's what I mean by, so you put data on here, which is consistent with question 2. So just consistent with this. So that, in other words, the only thing that's fixed here, so there's just some things that are fixed, like, this torsion should equal to 0 at this sphere. At this sphere, there was trace chi should equal that value 2k over minus u, etc. Right? So chi hat is free. Chi hat is free because we compute it. Chi hat's free. Okay, so you put data, basically any data you want there. Okay, you just need this torsion to be 0, this to be 0, this to satisfy this right thing. And then, okay, and then you can say, fine, now what do I do? Now you can now you apply well-posedness of the characteristic initial value problem. Okay, of course that you can only apply on any finite piece of this, right? So what that says, so I can, at any finite piece, I can run that theorem that we spent all that time doing, and I get some neighborhood, some solution in some neighborhood of this, right? Of course, the size of that thing can depend on where I stop. But then I can do it for all the way up to there. It's just that this thing might get very, very, might get very small. So I have a solution here. Okay. All right. Now, Okay, but we know that's sort of the natural thing. So if I was going to get a self-similar solution, then this is a very like abnormal region to solve for. In reality, what I should be able to do, and we saw this explicitly with Christodoulou's ones, but from the scaling, but it makes sense is I should be able to construct space-time up to say v over minus u equals some delta, where delta is small but zero depending on the data. So you can either think this is just exactly what happens in Christodoulou. So remember, so v equals u equals a constant are just these rays, right? And so, I mean, so again, everything is dilation invariant along a ray if you're exactly self-similar. So if you're exactly self-similar and something bad, I mean, if you're exactly self-similar and you exist here, then you have to exist on the ray just because you have some scaling. So things go wrong only as you move this angle. All right, so this is the first thing you can try to do is, well, prove that this solution actually exists up to some v equals v over minus u equals delta for some sufficiently small delta. Okay, so well, so you should be able to do that. So let's say, so step one, prove that. All right, how do you prove that? Well, we know that everything boils down to a priori estimates. So what you can do is you draw, so in this, so you have this region. Again, using the same kind of, everything boils down to a priori estimates again. And the name of the game is just basically you have to pick, you draw any rectangle that you can draw. So here you have, so here's this v over u equals delta. And what you have to do is any rectangle that you can draw inside here. So here's some rectangle R. You need to basically you need to run some, bootstrap argument like we did in the characteristic initial value problem and show that you can uniformly control things in some norm in this region. I mean, whatever, something like that, Okay, we'll talk about the norms that you do that with maybe next time, by the time I get to the end here, we'll see. All right, so you want to prove that you do here. You also want to, not only that, you want to do this with norms. When you do this, you want to use norms which are actually scale invariant. You want to do it with the ones that are kind of like correct. All right, so you're going to establish, estimates. And these rectangles are. Again, it's the usual thing that in each of those rectangles, like you have this region that you get at first. And what you do is you can at first just pick a rectangle that's in the region where the original local existence works. And then you prove some estimate uniformly up to that. And then that allows you to go further because you'll have some quantitative control, et cetera, et cetera. So you establish estimates in here and you want to use norms which sort of respect the scaling, What does that mean? So that means that they should sort of stay invariant. They should stay they should stay invariant under, they should be norms that would stay invariant if you were if you were self-similar. If you were self-similar, and if you did the scaling change of variables. Okay, again, that's a little abstract. Let's just be very concrete. So, e.g., when you prove pointwise bounds for Ricci coefficients, should be of this form. You're not going to prove that this is less than something. Well, first of all, you won't be able to prove that this C is uniformly bounded everywhere because already on the V equals 0, it behaves like 1 over U, right? But the scale invariant thing would be to prove that U times this, that this sup of this in your region, that this is less than something depending on data, right? This is what I mean by scale. These are scale invariant bounds. So if the thing behaves in a self-similar way, you put some weights in so that it scales, that it makes sense. All right, so those estimates you prove in there have to incorporate weights to do that. That's not some obvious thing that would work, of course. All right, and then similarly for the energy estimates. Right, we did energy estimates for curvature. So those are now integrated, but again, they will transform, and you can compute under this change of variables. It's not too hard to see how you have v integrals, u integrals, some u's and v's pop out in different places. You want to put weights in those estimates so that the things respect the scaling. Right. So if you do that, then like this is kind of the sharpest bound in some sense you could possibly do, at least of this form. Okay, that's step one. Now already there, you could now to try to construct. Well, okay, let me not get ahead of myself. All right, so once you've done this, suppose you've done that, then you'll have, some solution up to here. So this is all flat, but let's just draw here. This is say u equals -1. All right, and you have a solution here, right? So then I could always, from my solution, so remember there's this fundamental, the thing which is behind all of the scaling, which is that, so from here, I can define, a new metric, a new solution, by, again, do this change of coordinates and then divide by, then divide by lambda squared. Right, this uses, so of course, if I have a solution in one set of coordinates, I do a coordinate change, of course, I still solve the Einstein equations. And then there's also this fact, right, that if, Ricci of a constant time, if, equals 0, if, right, if Ricci, if A is a constant, right? Okay. So I can do this change of coordinates that'll still solve it. I can divide by this, that still solves it. So I can define a new solution. We can call this G lambda. Then here's one of those cases where I always do you take lambda to 0, lambda to infinity? One of those endlessly confusing questions. So let's think about it. So if we if originally you went from 0 to -1, then uh then that means so lambda u can go from 0 to -1 over lambda. All right, so if I wanted to get an existence on a whole, right? Again, if you're self-similar, then there's no reason you wouldn't stop here, right? You should just be this whole array. So that suggests I want to take lambda to 0, right? So all right, so I have the sequence of solutions. You have the sequence of solutions. Each of these will be defined on, you can think it this way, will be defined on, so this range doesn't change. Right, because this constraint is scale invariant. So if u scales, if v scales, it cancels. And then, but this one will increase. So it'll be defined here, intersect, say u in, oh, I sort of wrote this. Normal people write it like this, right? I also make that mistake a real lot. Okay, so this will be defined, well, not at 0. I guess, so let's do that. All right, will be defined like this. So this region, so each of these G lambdas, it's like you're getting really far down, Well, this thing's flat, you can always just add on the trivial part. All right, and then now the natural thing is you want to take lambda to 0 and get something to converge. Now there are two steps. You could try to run, well, this is not unreasonable. So you could run some kind of compactness argument. You could prove, if you prove, estimates for each of these G lambdas at for a sufficiently high number of derivatives, you do some kind of Arzela-Ascoli, thing at the end, and get some subsequence where these things converge and argue that they solve, that they the limiting object solves the Einstein equation. So you can do that. But there's sort of better way to approach it. There's a way to prove something sort of better and which has implications in other settings, which is the following. So you can always, whenever you do these kind of compactness arguments, again, there's always this thing that, does it depend on the limit, whatever, it's hard to characterize. It could depend on the subsequence that you took, right? In this case, it shouldn't, it won't. Well, I mean, secretly we know, well, I guess I've erased everything, but we know that when we did the formal computations, um, the only freedom was chi-hat, right? So what it would be very natural to conjecture that the self-similar solution, so this limits that you take, for example, should only depend on the choice of chi-hat. So you can you should be able to read off from your very first thing that you did. So here this was free. So whatever you picked here, and again, only at the initial sphere, that should be the only thing that affects the limit. And you want to prove that. So how do we prove that? Well, the idea is you want to establish, directly, some estimate for, say, G lambda 1, minus G lambda 2 with these, again, where all the lambda i's are, say, going to 0. Right. You should stop me immediately and say, what are you talking about? Like, you're not supposed to take the difference of two metrics, right? That's weird. Well, of course, but if you fix them, but we have a fixed set coordinate, we have some fixed coordinate systems where we have these explicitly, we take the difference in their common domain of validity in the UV. All right. And the idea is, so we want to do that, and we want to establish, and we want to estimate these in a norm which sort of vanishes as you rescale it. Vanishes as you rescale it. All right. So what? 448. Okay. So what do I mean? Again, that's a very vague statement. But let me just talk about something explicit back here. All right. So remember back here, I said that we prove a priori estimates, and we want to prove like the best one you can that's consistent with scaling. So for example, you want to ultimately be able to say that all the Ricci coefficients, if you take their norm, multiply it by u, that's bounded. Okay. And this is like reasonable because at v equals 0, this is true that this scales like a constant, at least for some of them. And so you can't do better than that. But, all right, so, okay, so what do we mean? Well, okay, so go back to estimates for G. And suppose that along v equals 0, all the Ricci coefficients, the Ricci coefficients somehow, had sort of, had bounds which were less singular than the self-similar rate. Okay, so you can consider, there are different ways to imagine this, but I mean, you could, yeah, let's not even worry about whether or not you can actually construct characteristic data where this happened. Just suppose such a thing existed. So for example, that in particular, when you put all of these at v equals 0, it was no longer the case that the best was 1 over u. Maybe now you have 1 over u to the minus 1 and you gain something, plus some epsilon. Suppose you had that for some epsilon. All right. Then, it might be reasonable to you could ask yourself, can I propagate that? In other words, so assume I have, I gain all the things scale a little better. I have upper bounds, which are a little better. Then now when I do all of this stuff, I could say, well, maybe I can do a little better here. So I could try to do a little better. All right. So suppose you had this, you could prove bounds, which have an improved scaling. Okay, which sort of gain. All right. And the point is that so you'd prove, so then you might prove, for example, again, you need to do the analogs for the energy norms and everything. I'm just writing one of the norms that shows up. You might prove, then now this soup, is bounded by data. And this is a better estimate because this weight degenerates less fast as it goes to zero, right? Okay, but now what you can see is that somehow, because this thing degenerates like less better, when you do, if something, if you had a metric sort of which was you controlled in such a norm, then when you start doing these rescalings, so before, each of these G lambdas, I could, of course, when I do that rescaling for the G lambda, the data along V equals 0, of course, stays exactly the same because it's scale invariant. I mean, that's exactly right. And so there's not like, and then I could I could do that rescaling. Basically, I can rerun this argument and get like the same bound. But if you sort of broke scale invariance like this, see now when I rescale, if I rescale here, then somehow, if the natural scaling is that this u times this thing is left invariant, but now when I rescale, because of this epsilon, you might pick up, say, a minus epsilon, which you could then, if I scaled by epsilon, and then you might put that on the other side. That's lambda to the epsilon times d. So now it would look like, so if I could do, again, it's not even clear that I could ever set up data like this. This is just a weird, we're just contemplating this kind of situation. So for some reason, these things satisfied a better bound, well, then I could maybe propagate this better bound. And then when I rescale it, sort of, it would just automatically, then I would have to sort of go to 0 as I do this rescaling. It kind of makes sense if you think about it, right? All right, but okay, now let's put all these things together. But the point is that if you look at, say, a G lambda 1, so you rescale G lambda 1, and these two rescaled metrics exactly, well, they don't exactly agree. The self-similar part of them will exactly agree at V equals 0. And the only thing, so along V equals 0, these have to be, something with better than self-similar bounds. All right, again, what do I mean? So I mean that you sort of formally look at like the Ricci coefficient for this. So you rescale this, look at say chi hat bar. Well, those are 0. Look at chi hat, or even like a derivative of chi hat. Yeah, let's look at dv, make it interesting. Well, we could look at all these things. So we could look at chi hat on v equals 0. That one we know exactly behaves in the self-similar fashion, right? So these two will just be when I rescale them, chi hats are the same. So I take this difference, again, it's not really a metric, but formally I just take the difference of all the equations. And so somehow the difference of the two chi hats will be 0. So all right, that killed the self-similar freedom. Now you look at things like little omega. Little omega, remember, you could add this constant, right? So that those constants might be different when you do these rescalings. But the things, well, now the difference will be something better, will be something better than there you didn't have a self-similar freedom, so you don't get it. So the point is, so anywhere where there was something exactly self-similar at v equals 0, these two rescalings, when you take the difference, those things cancel. So now this scheme, if you had a scheme like this is what you could do is sort of take, you look at again, difference of the metrics doesn't really make sense, but you just take all of the double null equations and you just take differences of all of the things. It's a huge, big mess. All right. But, depending on how flexible your scheme is, you could then try to run a scheme like this. And you prove that for this thing, for this formal difference, you can prove some estimate for it, which gains a little bit from this scaling. And then if you can do that, this is what's nice. You only have to do that for some fixed scale. Like you just have to show that for, in other words, just for some lambda minus some, mu, you can prove something just with the weight, so where the weights gain an epsilon in some sense everywhere. Then automatically that will prove that the sequence is Cauchy because you just as taking these things down to zero just corresponds to rescaling everything. And because you sort of broke this scaling, the norms will sort of just automatically go to zero. All right, I'm going fast and trying to squeeze in at the end of the lecture. Sorry about that. Basically that's what works. But I guess I don't really have time to tell you too many details of it. Okay, but this procedure does work. All right. Yeah, so maybe questions? I could say in 2 seconds something about something about like the estimates, I guess, the last few minutes. All right, I'll hang around a bit after if you have questions. All right, so let me say something about, all right, these are a lot of abstract words. Of course, we know we did the characteristic initial value problem. We know that all the work is like, you actually have to do these estimates, and lots of the structures, the kind of structures that we use when we did the characteristic initial value problem are relevant here. So I'm really running out of time, but yeah, I'll just say the following. That like in the characteristic initial value problem, okay, so now, of course, all that stuff I did before, I did with the hypersurface going the other way. Now it's going this way. So remember we did these other problems, the Nobel 3 equations were good, right? Those were sort of easy ones. The analog here is Nobel 4 equations. These are good. Because somehow you integrate from, well, I don't know, don't really have. You can think now, and now you sort of gain smallness because you integrate that way and you sort of gain some smallness like with the other problem. And, like in the other stuff we talked about, these are scary. Right? And we know that from all this the jet computation we were talking about, because when you have a Nobel 3 equation, even at the level of characteristic data, you're inverting some operator like this, it really matters what the C is. Some sense we've kind of okay, yeah. All right. And so now the name of the game is, well, basically, when you have things like this, it's usually good. But you go to something like this and you want to, let's say you have to invert a Nobel 3 equation to estimate some Ricci coefficient, equal some stuff, prove doing some bootstrap argument. All right. So again, well, this thing, C is negative, remember? So you can't just multiply by C naively, everywhere and then integrate this, because this term sort of has the wrong sign. And you can't, even if you think about Gronwall says you can, if you put this term, if you put on the other side, right, that you can, you're less than e to the, integral of the coefficient, but this 1 over u is exactly going to give you a log, right? So that's bad. So you have to sort of, come to terms with this. So basically, one of the only games in town is you can try to multiply this, multiply through by some power. And then, that will shift things, right? Yeah, whatever. Well, u to the a. All right, and so in principle, now if this a is like big enough, depending on what c is, you can make it so that this term sort of has the other sign. Remember, u is negative, and then you could just multiply this with u to the a psi, integrate, this term is good, whatever, everything's great. Except it's not that simple, because it's very important that all this scaling I talked about. There are very specific scaling things you have to make sure you understand. And so it's not quite that simple, but there's one slight other thing that you can do, which is not obvious, which is you can throw in some v weights. So you don't, so maybe it's hard to prove that this is bounded, but maybe what you can do is sometimes you can do this. You can subtract off this at v equals 0. So this is sort of another trick, right? And then now that this vanishes as v goes to 0, you can put this and you can say, for example, you could divide by v. Because this thing will be finite at the initial data in some sense. Well, not some sense, it will be, right? Because because this say vanishes. And so this is a trick. So if you sort of felt like you needed to multiply, for example, by u squared in order to cure some term being of the wrong sign, one trick that you can do is, well, maybe that Ricci coefficient vanishes. So that actually happens in this. So if you remember, we had derived, I told you there was this term there was something like this on v equals 0. So in particular, there's this thing is big. 3 is a lot bigger than 1, right? Right? So you say, okay, well, one thing I could do is multiply this by like u cubed, and then that would eliminate that. But the u cubed is really bad because I want to prove ultimately that u times torsion is bounded. All right, so I kind of want to do that, but you know, maybe I can, if I just multiply through everything by v squared, you know, then think it might work. Anyway, so that's, so I've run out of time. But there's this kind of trick, which basically, and there's a similar thing with the energy estimates. So you write down these norms. So the constraint of your norms being scale invariant imposes that you have to put in weights, but the weights are kind of rigid. In principle, if you just use u weights, it's kind of rigid. Then you realize there's this trick that if you take advantage of, so torsion vanishes if u equals 0. We showed that, right? Um, and when we set up our problem, we pick torsion to vanish. So then you play some games. So sometimes things seem like they won't work, but then you try to exploit that, something vanishes, and if something vanishes, you're sort of allowed to put a negative v weight, and somehow because the v squared scales like u squared, now this is something which this quantity scales just like u. And so anyway, this is, of course, now the name of the game is you have to find a scheme which works not only for these linear parts, but there are nonlinearities everywhere. And so, if you use this to deal with some term here, then this weight has to go on some nonlinear terms and everything has to work out. But again, just sort of have to believe me, of course, it's more complicated than that characteristic initial value problem that we did. But a lot of it's the same. You can use the same kind of signature consideration. So these weight schemes, how many V weights, where, whatever, involve some signature, for example, and you can use that to sort of, understand, to basically show that it works out. So if you put some V weight here, you have the nonlinearity, something has to be able to take the V weight. You would sort of nothing, you would, your scheme would collapse if none of those terms vanish to v equals 0, but signature will tell you that, it's all consistent in some way. All right. But of course you have to, this is like a 80-page paper or something. So I mean, it's not trivial, but it's like a similar, sort of similar. Okay, so let me end here. I'll hang around for a few minutes.